Hello everyone, and welcome to this next video in the Foundation module. In this video, we are going to start working on the basic integration for our elevators and our staircases. Now, in the last video, we took care of integrating the building into the Unreal Engine, so we now have our tiles and floors properly set up, our normals are dealt with, and we have a basic collision mesh. So if I go ahead and play, we can now enter our building, and that's all working just fine. But of course, we still don't actually have a way to reach any of the upper floors. So that's what we're going to start working on today. If I go to the upper floors, of course, we do have them. But to reach them, we're going to have to integrate different parts into our building. And that includes cutting holes into the floors to allow the player to pass through. We are going to have to create a control system to actually decide where those holes should be. And we also need to make sure that this all sits on a grid, so we don't have elevators and staircases intersecting with one another in weird ways. Now, in order to do this, let's go ahead and look at our tool here in the example file. Now, as you can see in the example file, we do actually already have a control system set up. And this is based on the same control curves that we use to draw the bottom of our building. Now, if I grab this control point and I move it over, you will see that the staircase is going to move along and everything is going to adjust to it. Now, on the other hand, here the elevator is using a different control method, which we will also set up, and this involves an external object, such as a basic Unreal cube, that we've dragged into the scene and then hooked up to our tool using the Setup tab down here. Now, if I grab this cube and I move it around, then just like the staircase, it will update the position of our elevator. Now, the elevator and staircase are built into an internal grid in our building. Let me show you the visualizer, and if I turn that on, you can see that it actually shows us where the elevator and staircase are pointing. Depending on the location of our control objects, such as here, if I move it to one of these other edges, it will change the direction of our elevator, for example. So that's one way we are going to be able to control this system. Next to that, the elevators and the staircases are completely optional components of the building. So we can actually remove them. If I go over to the elevator and staircase tab, I have the ability to turn off one or both of the modules. So if I turn them off and hide them, you can see that we have actually punched holes straight to our building where the elevators and staircases can actually exist. Now, this is going to, of course, be useful for us to traverse floors because we cannot go through a solid mesh, but it's also useful when we combine it with future modules of the master class. I'll quickly show you what I'm talking about, and then we're going to go straight into the lecture. I'll talk about this more later as we complete this foundation project, but in the next module of the master class, which is going to be called Ascension, we are going to build a fully functional elevator and staircase tool that will allow us to traverse up our building using blueprints and much more detailed mesh instancing. Now, we haven't gotten to this part just yet, but if I go ahead and play inside of this tool and I go into our building, then you can see that I do actually have a fully functional elevator right here. If I go ahead and go inside, I can go and select a different floor using the blueprint controls. And within just a few seconds, we'll be on the 4th floor of the building. That's quite nice. Then next to this, we also have a fully functional staircase that we'll be building in the next module. And in this case, we have full sets of instances already working. We'll have lights as well as signage. And if I go up to the top floor, we'll have a dedicated module up there too with a skylight. Now, I will explore more what this module has to offer by the end of the foundation project. And at this point, I'm still working on developing it and recording it. But it will be due for a couple months after the foundation module is completed. Alright, so let's move over to Houdini and let's have a look at the example file to see what exactly we'll be building today. So in this video, we are going to cover a couple of new concepts, including some more VEX. We are also going to deal with Booleans, and we are going to deal with a couple of techniques that will allow us to build the control system. So the part that we'll be building today mostly resides up here, this part of the network. And this will involve the creation of an internal grid for our building. And then we will take that grid and snap points to it. And this will allow us to control where our elevators and our staircases are actually going to go. These points will also have an orientation, so our copy to point system will allow us to later copy a couple of boxes to them that we can then use as temporary placeholders for our elevators and staircases. Now, these boxes are going to be able to be imported over here in this side of the network. I'm going to grab them with an object merge. And then I'm going to use a Boolean node to cut holes into the floors of our building. Like so. And this will later, of course, house the elevator and staircase parts of the tool. Now, everything that we're going to do in this video will help us further on when we work on the other parts of the building, such as the detailed versions of our staircases and elevators, but also the objects that reside on our roof, the visual elements on our building, such as these visualizers, and the pillars inside. So let's go over to our main Houdini session, and let's get started on building this system. Okay, so the first thing we need to do, like I said, is create the internal grid for our building. And for this, our building is a little too small. So let me go ahead and expand it a little bit more so we have some more space to work with. Let's go to the object level and then go to the building shape. And I'm going to grab my control curve and I'm going to simply drag it out to create some more space. Now, if the tool ends up being a little too slow for you, you can make the tool a bit faster by simply switching it to one floor. And this will reduce the amount of tiles that you have to work with, and it will speed up the tool a bit. We can of course increase the amount of floors later. And at the end of this module, I will talk about how we can potentially optimize the tool to make it faster. In fact, we'll make that into a homework assignment. Okay, so if the size of my building expanded a bit, let's go ahead and give it some more height again. And now we should be ready to start working on the interior grid. So let's go ahead and dive right back into our tool. And the next section that I'm going to build will reside right here. So I'm going to make my screen a little bit bigger, give myself a bit more space in my network view. And let's zoom in here and create a new netbox. Now I'm going to make this netbox nice and big so we have enough space to work with. And I will call it the interior grid. Next, let's drag a line from here, where our end node is, and let's pull it over to the right. And personally, I like to add a dot, so I keep my lines horizontal or more diagonal, so it stays organized. Let's press the Alt key, and then add a dot over here, and then drag one down. Now, if you're ready with that, you can press Escape, and then you can let go of it, and it will stay there. So we can now pull data from it. Now the next section that I want to do is add a flatten node, just like we did before, because this curve isn't guaranteed to be completely flat. In fact, even if it is flat, like I mentioned before, it might actually have some very low fraction values that we need to fix. So before we use the transform node, in this case I'm going to use the simple point expression to flatten the point position down to 0. So I'm going to copy this Wrangle node here from the previous example, and let's paste it in right here. Now I don't need this dot here right now, so let's get rid of that. And I'm going to call this node the flatten node. All right. So next, now that we have our ground plane, and I don't really care which orientation it has, if it's facing up or downward, I only care about its shape. So with that, let's go ahead and create a new grid for inside of this shape. And then we'll cut that grid using this one. Because it's perfectly flat, this will work. So first, let's go ahead and create a new grid node. And I'm going to call this grid node the interior grid base. Now, this grid base is going to have to cover the entire floor of our building. And to do that, we can use the bounding box expression like we've used before. And in this case, we are going to use the bounding box size function. So let's create a spare input link between these two nodes. So this grid is going to know the bounding box of my flattened node using the -1 reference. Let's add a spare input. Let's grab the flattened node here and let's just plug this in. And now up here in my size values, what I want to do is type bounding box -1, because we are now referencing the spare input over here. And then d_x size, all capitalized. And if we do that, it's going to cause our plane to match the size of our grid over here. So that's the start. Then let's copy this. Let's paste it to the right on the y value as well. In this case, I need to change this to the z value. Now, just to make sure you understand what I'm talking about, when we look at the size of our grid, the grid here actually only has 2 dimensions, the first and second dimension, x and y. So over here, the size is actually size x and size y, right? These 2 channels. Now, I'm currently referencing the bounding box information from my original plane. And this one, if I look at the origin nomen, so with the D menu, of course has to reference the x size on this plane and the z size in world space. So that's actually what I meant with that. So by doing this, by sampling the size in world space, we can get the exact dimensions of our ground plane. Now from there, we actually still need to center this grid on the middle of our ground plane. And we can do that using the centroid expression. Now the centroid expression is written very similar to the bounding box expression. If we type centroid into the x channel, we can then reference the node, which in this case is -1. And then I'm simply going to say, comma, d_x. If I do that, it's going to give the exact center of our grid right here. And then I can copy that, plug it into our z channel, and then reference the z center position. So with that, no matter where our original input shape is located, this grid will always reside exactly on top of it. Okay? Now, next, what I would like to do is increase the amount of rows and columns directly proportional to the size of this grid. Because as we draw a bigger building, we will need more detail. And we'll need this to turn it into an interior grid later. So let's grab the size X channel. We can do that by hovering our mouse over the left channel here. Copy that parameter. And then I'm going to go to the columns section, which is inside the X direction here. And we're going to paste that right there. Then let's copy that, go to our rows, and let's set that to the size Y channel. And this will add some much needed detail to our grid. Now let me go ahead and hide my origin nomen again, because it's getting in my way. And also I'm going to flip around my render and template flag here, just to make it a little bit clearer as to where my grid is located on my original shape. Now at this point, this interior grid is still far too dense. Each grid section here is currently about 1 meter in size, and they need to be at least 3 to 4 meters in order to work for elevators or staircases. And I also want them to be exact, because at this point they're not even exactly 1 meter in size, because the way how it's set up here. I won't go too far into that right now, but the idea here is that I want to take this grid and snap it to a much larger virtual grid. And we can do that very simply using a fuse node. So let's go ahead and create a fuse node. Plug that in below. And then over here on the right, under snap to, I'm going to switch this over to grid mode. Then I can take this and I can actually set a much larger scale for it to snap to. So in this case, I'm going to switch it to 4 meters in the X and Z direction. And we do need to provide it with an upward snapping set. Now I don't really care about what it is as long as it's not 0. Because if you set this to 0, then it will simply stop working. So let's set it to about 1, because I simply want to snap it to the grid position, and this will always work. Next to this, we can use the grid offset to move this grid over. And you can kind of see how this is going to work. As I move my offset around, each point in this grid is going to start snapping to this virtual grid inside of this fuse node. And based on where the original grid points were located, they're going to reposition themselves to match. Now at this point, the points are actually fusing, and that's good, because that means that we don't have to worry about it. If we weren't fusing them, you see how they all start overlapping each other and basically re-topologizing. We don't want that, so let's keep it nice and fused. So with this, let's go ahead and add this to our control system, because I would like to be able to control the exact size of my grid and its offset from my interface. Let's open up the type properties. And in here, I'm going to create a new folder for the elevators and staircases. So let's go ahead and grab a new folder, and let's drag it up here above our setup tab. And I'm going to call this one elevators and staircases. Now the first thing I want to add in here is a float parameter. And I'm going to call this float parameter the interior grid scale. So that will control the actual scale of our grid over here. So next, let's go ahead and decide the minimum size of our grid. Now, the grid can't be too small, because if we do that, then it won't be very useful. Anything under 2 meters, in fact, probably won't work for the player anyway. Now for the main project of the masterclass, I'm going to use a size of 4 meters. But we could go also to 3 meters, and that will still work. Parts of the toolset, especially the next module with the elevator and the staircase, will have support for 3 and 4 meter sizes. But like I said, anything below that is going to be problematic. So let's lock it here at 3 meters minimum. And I'm going to set the default value to 4 meters. So with that set up, the next thing I want to do is add a grid offset as well. And we only need this to be in the X and Z direction. So let's add a float vector 2 here. Now I'm going to call this one the grid offset. Now next, let's set up the range. So I'm going to set this to -4 and 4 respectively. And this will match our default interior grid scale. Now I'm not going to lock it, because if we make the grid larger, then I still need to be able to make that work. But for our default values, we're just going to leave it at 0. Now with that, let's go ahead and apply these changes for accept. And we now should have our controls over here in our parameters. Let's open those up. And let's go to the elevator and staircases tab. And now we need to hook it up to our fuse node here. Now I'm going to call this fuse node the snap interior grid fuse node. And let's grab the interior grid scale. And I want to hook it up to my grid spacing over here. So let's plug it into the X channel and also the Z channel. So now if I change this, it will cause my grid to scale up and down as I want it to. Then next, we also need to make sure that our offset will work. Now the offset on the snap function is based on a 0 to 1 range. If I move this over from 0 to 1, a value of 1 will basically move over my grid an exact 1 unit grid space. So in this case, 4 meters. What I want to do is link this up as meters. So what we need to do is grab one of our offsets here, like the X channel, paste that in, and then simply divide it by the interior grid scale. So let's grab the interior grid scale, and then I'm simply going to say grid offset X divided by that, and that will give us a fraction value. So if I go ahead and set this to a value of 1, then this will return, in this case, 1/4. Let's copy this, paste it into the Z channel, and I'm just going to set grid offset X to Z. Now with that, we should now have our basic grid working, though it isn't quite finished yet. Let me hide my grid and I'll show you what I mean. So if I look at the actual building shape, you can see that the grid node, its snap feature, has moved all my points onto this new virtual grid. And unfortunately, in some cases, it has actually moved it inside of my building shape, like this. We need to fix that. And the best way to do that is by simply making our interior grid a little bit bigger. So let's copy our interior grid scale, go to our interior grid base, and I simply want to scale up its default size over here. So let's make it just a bit bigger. Let's add to the bounding box size in X the interior grid scale, and that will already work to some extent. But just to be sure, I'm going to scale this up sufficiently so we don't have to worry about it. I'm going to just say times 6. That's more than enough. And then I'm going to add it inside brackets just to make sure that the math priority is always set up properly. Then let's copy it, paste it in the Z channel, make sure it's referring the Z channel properly. And there we go. Now we should have our grid covering the entire floor plane. Okay, so with that set up, let's go ahead and try it out. So let's open up our parameter panel. And over here, if I change the interior grid scale, okay, that seems to be working. It's staying outside of our ground plane as well, so that's good. Now let's test out the offset. So offset X works, okay. And offset Y does not. Okay, so in this case, it seems I've made a mistake, right? And this is easy to do because what I did is I simply copied from here my entire expression, pasted it in here, and then quickly filled out X to Z. Now there is no grid offset Z here because this is a float vector 2, and that one automatically names them X and Y. Okay, so this will simply return a value of 0. Now, if you're doing this and you actually want to make sure that you're referencing a correct value, you can simply check while you're typing, and it will give you actual parameters that you can grab if they exist at this address. So in this case, I could simply click on grid offset Y, double click, and it will automatically set it up. So that will help you make sure that when you're typing in references manually, you're actually grabbing one that exists. As long as it exists at that very moment, it will be able to find it. So now it is working. Okay, so all of our offsets and our grid size are now working. Let's go ahead and continue. Now at this point, we can actually continue. We can take this grid and cut it with our ground plane. But before I do that, I quickly want to introduce you to a little bit of VEX code, because VEX code is very useful and we can use it to replicate the functions of this fuse node here. So if you want to continue, you can skip to the next section of this video, but I suggest you watch this because we are actually going to use VEX a few times in this lecture, and I think it's a good idea for you to get familiar with it right now, okay? So the equation that we're going to write is up here, this part, and I'll explain in a second how exactly it works, and then we'll build it. But over here I have my grid size, just like with my snap node, with my fuse node, and it allows me to change the scale of my grid, and we also have the offset values right here. Now you might have noticed that if I scale my grid, you get these connections that sometimes interconnect in a weird way. This is actually a graphics glitch. I mean, it threw me for a loop when I first saw this, and I was like, okay, why is it doing this? Turns out it's not actually doing it, it's just how the viewport draws this. Because the moment I plug this in to, say, the rest of my network here, it still returns squares, okay? So this here, it's just a graphics glitch. In fact, if I go ahead and change it around, and then I click on it again, you can see how the graphics glitch is actually gone. So in this case, don't worry about it, right? Under normal circumstances, this might be a problem, maybe something's wrong with our equation, but in this case, it's not. It's just a graphics error. So let me quickly explain to you how this script here works and how it's used to snap our grid points to a particular value. So let's open up my drawing board and add a couple of points. And I have a couple of them drawn already. So we have 7 points here. Each one is located at its own coordinate, so coordinate 0, 1, 2, etc. Now let's say we want to snap to a range of 3. So that would mean that if I draw a line, the first snap would be between 0 and 3, then 3 to 6, and then 6 would go to 9, okay? So that would go outside of my screen. Now in this case, that would mean that our points here would each assign themselves to one of these intervals. So 0 will become 0, 1 will become 0, 2, 3, and 4 will become 3, and 5, 6, and 7 will become 6. Okay, so that's relatively simple. It will just snap to its closest point. Now, if you want to make this work with VEX, with an equation, with math, then the best way to do that is to simply collapse everything in this range down to a range from 0 to 1. So basically, this would become 0, this would become 1, this would be 2, and then 9 would be 3, right? And then you can simply round to an integer, meaning that if we snap these points, 0 would be 0, 1 would be 0, 2 would be 1, 3 would be 1, 4 would be 1, etc. Right? So if we grab this entire range and divide it by 3, we will actually make it go from 0 to 1 instead of 0 to 3, right? Because 3 divided by 3 is 1. That's very simple. Now, of course, this works because we are actually dividing 3 by itself. So that will always become 1. And it will always snap to 1. But if we are grabbing any of these other values in between, it will return a different kind of value, right? So if we say grab 4, and we divide that by 3, we get a value much closer to, say, 1.33. And of course, this will continue on into infinity. Now what we want to do is grab that value and then round it back to its closest integer, which is going to be 1. And to do that, we need to actually wrap this equation here inside a round to integer expression. We can do that very simply using the rint VEX command. So if we use the round to integer VEX command, whatever's inside is going to automatically snap to a full value, in this case 1. Then, in order to return back a value to its full size, we simply have to multiply it again by the actual value that we wanted to snap to. So that would be, in this case, 3. So no matter what we get, right? If we have 5, this will become 6. If we get 7, this will become 6. So no matter what we get, it's always going to round to that value. Okay, so let's go ahead and build this in Houdini. Over here, let's create a new attribute Wrangle node. And I want to plug it in behind our grid. Now I'm going to call this one the snap interior grid alternative. Now each one of the points on this grid has a point position, as you can see down here. So we want to access that point position, and we can do that using the v@p expression. And then if we add a semicolon to the end, we actually complete the line. So this will basically talk to the entire vector point position attribute. Now we want to split this up, so we're talking to the individual components. So let's say v@p.x, and let's copy that. Then we're going to do v@p.y and v@p.z. So each one of those talks to each individual channel of this point position. Now right now we're not actually doing anything with that. All we're doing is calling the attribute and its individual channels. Now at this point we can actually add a value to these, right? So if we say v@p.y is 4, we will actually raise the entire grid up to 4 because all the y channels are raised up to a height of 4. This is very similar to what we did before here with the flatten node, where we flatten everything down to grid level. Now I don't actually want to do that. Let's set it back to 0. But for the x and z channels, what we want to do is actually grab the original positions, right? So let's say v@p.x is v@p.x. So we're basically calling the attribute, and then we're setting it back to itself. And of course this won't change anything, but at this point I could say add a value of 5. And this will offset it, right? This will offset the entire grid over by 5 units. We could also write this a different way. We can say v@p.x is plus equals 5. And this will do the same thing. We could also say minus equals 5. And that will subtract it, or multiply, or divide. So we're actually scaling our point position. But that gets a little bit outside of the point. In this case, let's go ahead and place back our v@p.x right there. And now, what I want to do, like before, like I showed you, is I want to take our value and divide it by whatever value we want to snap to. So in this case, that would be 3. So let's go ahead and add a channel float reference expression. We can do this very simply. Let's type divide by, and then CHF, or channel float, and then within brackets and quotation marks, we can give it a name. So in this case, that will be grid size. All right. So with that, it's now looking for a parameter on the node, and we can create one really quickly by pressing the button here on the right. So there we have one. Now at this point, the value is 0, so you cannot actually divide by 0. That's actually a thing, right? Let's scale this up a bit. Let's set it to 3. Okay. So now if we look at our grid, well, you can see it's scaled everything down. Then next, let's go ahead and add our round function around it, rint. So let's type round to integer. And as you can see, the card says rounds the number to the closest whole number. Okay. And then we can simply wrap this inside of that expression. like so. Now you can see here, all my points have now snapped to the individual elements on my grid. And down here, the X values are all now whole numbers. Then let's go ahead and grab the grid size again. And behind this bracket, behind the bracket for a round integer, I'm going to multiply that with its own grid size. And now you can see that all my points have snapped to every third grid element. So it's working, right? We are actually snapping to every 3 units, just like we wanted here. Now let's go ahead and copy this up to the equal symbol, grab this and replace it. And then I'm going to change the point position here to Z. Okay, so now we have our basic snapping behavior working. Now this is good, this is working. Next, let's go ahead and add the offset component as well. And for that we can very simply, just behind all of this code, say plus, and then let's say channel reference float offset X. And let's create that. And now we should be able to move the entire grid, but we don't want to actually move it past itself, right? Because if we do, at some point, it's going to simply move off of our existing shape. We want it to stay there. And the best way to do that is to use a modulo operator. Basically, you can use the percentage symbol and you add a value behind it. So let's say our grid size. Then what it's going to do is, as we raise the number over 3, it's simply going to start back at 0 again. So if the value goes to 3, it will actually return a value of 0. And then if we go to 4, it will return a value of 1. So if we look at this here, all it would basically do is it goes from 0 to 1 to 2, and then once it reaches 3, it loops back to 0 and starts back over again. So 7 will return 1, 8 will return 2, 9 will return 0. Okay? So with this, if we add this 2 to the other channel, and we make sure that we have offset Z in this case, and we create that, then now we do have the ability to offset our grid, and it will work just fine. So that's the alternative method of writing this in VEX. Now let's quickly hook this up to our interface as well, and then let's continue on with the rest. So let's just hook up the X channel to X and the channel to Z. Okay, so pretty simple. Once you know what you're doing, once you know how the equation works, VEX is pretty straightforward. It works similar to expressions, but there's a lot more to it. So we're slowly going to go into this, and I'll explain more to you as we go. Okay, the main thing about VEX to know at the very beginning is it always needs a semicolon in order to end the line, and you can add as many commands after each other as you want, but it always goes from top to bottom. So any value we change here will then be updated lower down the line, right? Anyway, let's move on. So the next part that I want to do, and I'm going to use my snap interior grid node here, is I want to take this grid that we have now, and I want to cut it with my original ground plane. So to do that, we can use a Boolean node. So let's go ahead and create a Boolean SOP. And just like before with the for each node, there are actually a couple of different versions of the Boolean node available. Now again, they're all presets. So the one that we want in this case is an intersect Boolean node. And the intersect Boolean node, if I plug this in, let's grab the grid here on the right, plug it into the first value. And then let's grab the second value, the original ground plane. Let's plug that into the second channel, geometry B. Now by default, our Boolean node isn't actually going to do anything. And that's because right now it's expecting a solid mesh. Now I'll explain in a moment what the Boolean node is actually trying to do here. But let's switch this over to surface first. Now as you can see, what it's basically done is it's taken our grid over here on the right and it's cut it with our plane. And as long as these two are overlapping precisely, the Boolean node should return whatever is overlapping because we're using the intersect function. Now there's a lot of features to the Boolean node and I'll quickly go over that. Let me quickly show you what the Boolean node is actually capable of. And over here I've created a couple of examples for us. But I also want to show you how we can potentially break it, right? Because there's several different ways how you can feed geometry to a Boolean operation. And while the Boolean node in Houdini is probably one of the most stable Boolean nodes I have ever seen and worked with, it's still possible to feed it geometry and actually break it. So let's go ahead and have a look. Up top here we have our flat surface shapes like we had over here. And the first one that we're looking at here is the union operation. And this one simply takes whatever meshes we feed it, in this case a grid and a circle, and it combines them. So you can see how it's intersected them here, right? If I take the grid and I reduce its sections, then now we have three primitives where they overlap and where they don't. So that's pretty useful. Next to that, we can grab the intersect feature, which does just exactly that. It takes the original shapes and wherever they overlap, it keeps them and the rest gets thrown away. Then we have the subtract feature. So we have our grid and then we have our circle and we're subtracting the circle from the grid. So eating away from it basically. And then last here we have the ability to create a seam. And the seam simply returns a curve object wherever these two objects intersect. Okay? So that's pretty useful. Likewise, we can switch this over to shader mode, in which case we take the original shape and we create a cut in it with the second shape. Now this was with a plane or in surface mode, basically a 2D object. We can do the same thing down here with 3D objects. So here I have a box and I have a torus. Let me just get close. And the first one here again combines them together. So in this case we don't have any internal geometry anymore, even though our torus originally did have it. And it simply merged these two objects together and created connecting polygonal geometry to make sure it's all valid. Next here we have again intersect, so we keep whatever's in between the two meshes. We can subtract, punching a hole in this box. And over here we have the seam again. So again, wherever both meshes intersect, it creates a polyline. Now the Boolean node can also take multiple meshes from input 1, such as for example here I have a box and I've copied it around in a circle using a copy and transform node and a couple of iterations. And I'm simply combining them using a Boolean in union mode. And if we do this, we will combine the meshes together, just like with our torus and our box. Now let's go ahead and see how this is merged. If I grab my reverse node here, I will turn all the faces on my mesh inside out. Then I can press the D button in the viewport. And under the Optimize tab, I can turn on Remove Back Faces. And this will simply remove all the polygons that are facing away from us. So that's pretty useful if you want to see inside something. Now in this case you can see that the mesh has been properly merged and in many cases you won't see any problems. In fact, if I look at the polygon numbers, we basically created an infinite torus of some kind, right? Now this works because in general, like I said, the Boolean is pretty stable, but it is possible to break it, and I'll show you how. Over here I have two boxes, one big box and one slightly smaller box, and these boxes are overlapping precisely. Like if I look at the numbers, I've basically overlapped them so different sides of this box are overlapping each other. Now at this point, if I use the union node, or in this case I've actually set it to subtract, it seems to be working fine, right? We're subtracting one box from the other. But the moment I grab my transform node here and I've hooked these up together and I rotate them, you'll see how it starts to break. Yeah, Booleans don't like it when you have exactly overlapping surfaces. When you have lines that overlap and there's just zero space between them. And the moment you start to rotate them in a different orientation than say a flat orientation or a straight line along one of the axes, it can cause some problems. Likewise, if we take some very complex geometry, like our little custom torus over here, or staircase, whatever you want to call this, and then we Boolean that, and then we take another one with a slight variation on it, so like this basically, and then we try to say subtract one from the other, well, it's going to cause some bad geometry as well. And in this case you can't even see all of it because I have my back faces turned off. Let's turn them back on. Now here you can see we have some Z fighting going on. We have some very thin pieces of geometry. It's an overall mess. So the moment you start to create very complex geometry and you start to apply a Boolean to it, it will still try to work. And in most cases, as long as you control what you're feeding it, it will work. But it's also possible to break it, especially when you get coincident faces, like in this case, where they just overlap. So that's a couple of the rules that you will need to keep in mind when you're using Booleans. They work best when the meshes don't overlap exactly, and they also work very well in cardinal angles. Otherwise, avoid feeding it bad or complex geometry. But alright, let's go ahead and continue with the lecture. I'm going to grab these and move them over to the side. And let's have a look back here at where we were working on our interior grid. So our interior grid has a lot of elements in it that we don't want to keep. We only want to keep the big squares that are fully solid. Okay, we don't want any of these half cuts. We don't want any of these small triangles here. So let's go ahead and get rid of those. And we can do that fairly easily. We simply need to measure the area for them and then subtract or remove any of the elements that are too small. So to do that, first let me give this a name. So I'll call this one the Boolean floor plan into grid. Right? And then next, let's create a measure SOP. And the measure SOP in this case is going to measure the area of each of our surfaces here. Now, when we measure the area, it's going to return to us a new primitive value that basically describes the total space inside one of our primitives. And if I look down the list, you'll see that some of them have values of 12 or 0.5, and the ones we really want in this case are values of 16, because our grid right now is a size of 4, which means that 4 times 4 is 16, right? So anything under 16 is actually cut into a smaller area, and we want to get rid of those. Okay, so let's do that. Let's go ahead and create an attribute Wrangle node. Let's go ahead and plug it in. And I'm going to call this one the isolate clean squares Wrangle node. Now in this case, what I want to do is grab the interior grid scale over here, multiply it by itself or by the power of 2, so we get the area from it, and then I want to compare it to the actual area on these grids here. Now I'm going to visualize those, so let's say I grab the info panel on one of these nodes, and then I'm going to click on area, and this will of course visualize our area attribute as a color. Then in the D menu, let's turn it over into a marker. So now we can see the actual size reflected as a value on our nodes. And you can see how some of these have very small fractional values, right? So we have 16, and this one's 16.00004. This one's, well, 4.00001. These values aren't quite exact. Now, in my experience, I actually believe that VEX is so accurate when it comes to decimal numbers that even if you were to compare two values that were rounded, it can still actually have problems with it. And some cases this is good, precision is useful, but in other cases, like in this case, it's actually a problem for us. And I'll quickly explain to you what that means. So over here, we have two numbers. We have one of our tiles, which is, 4 by 4, so 16. That's the value we're trying to compare. And this here is one of the area attributes that we're getting from our primitives. And it has that very small decimal fraction at the end. Now, we could try to round this number, meaning we can take it, like this value, and multiply it by 1,000, right? So we would get something like 16,000.00019. And then we could round it using a rind expression like we did before. And that would effectively turn it into that, right? 16,000 flat. Okay, sounds good so far. Then we can divide that again by 1,000. And that will turn it back into 16, or 16.000 in this case. Now, you would think that in general, if you compare 16 to 16.000, it will work fine. But unfortunately, that's not always the case. And while in theory this should work, in practice I found this type of comparison doesn't always function well. And I have yet to find a proper VEX function that actually does this decimal rounding for you. You always have to use this multiplication division trick. And using a direct comparison like this just doesn't work with this method, at least not as long as I've tried. So instead what we're going to do is we are simply going to take this value here, we're going to subtract 16 from it, and then we are going to say if that value is larger than a certain margin, then we remove the primitive. Okay, so let's have a quick look at what this means. Let's say we take this value and we subtract 16 from it. So that will become 0.00019. So that's a very small value, very close to actual 0, but not quite at 0, right? So we can't do a simple equals comparison to 0 either, because this will return a no answer, a negative. Instead, what we can do is we can take this value and check if it's inside of a threshold. So in this case, we can simply say, is this value greater than 0.001? And in this case, it is not, meaning that this tile is very close to 16. Of course, this only works if our value is actually above 16. If it gets below 16, it would fail, because, well, let's say we have a value of 10, and we subtract 16 from that, we are going to get -6. And -6 is still lower than our threshold value. So in order to fix that, what we want to do is take whatever comes out of our initial equation here, and we want to wrap it inside of an absolute block or an absolute function. Now the absolute function, or ABS, basically takes whatever equation we have, such as our 10 minus 16, which will normally return minus 6, but absolute is going to take that value and it's going to flip it positive. So in this case it becomes 6. So in that case, 6 is greater than 0.001. And if it is greater than that, we are going to simply remove that primitive. Okay? So let's go ahead and write that expression in VEX. Now over here, inside of my VEX node, first I want to create 2 local variables. And local variables in VEX are basically like attributes, except they don't interface with the attributes on our geometry. What they do is they store a value inside of our VEX code that can then be accessed and written to and read out from inside of the code itself. But it doesn't actually interface with any attributes, so it's actually pretty safe and clean if you don't want to accidentally override your values, right? Because it's very easy to do that with VEX if you're not careful. So in this case, in order to write a local variable, we simply have to type out the entire name. Whereas before we typed f@ in order to say grab the area attribute. What we can also do, if we want to create a local variable, is type simply float area. And this will do the same thing, except it will create a local variable that's only accessible inside of this code. Now in this case, let's go ahead and grab this float area attribute and let's stick it behind the current variable, local variable. So what we're basically doing here is we're grabbing the float area for whatever primitive we're running over, and we're storing it inside of this area local variable. Now the problem, of course, with our local variables here is that in order to actually get them back out, we have to either write them back to an attribute or we need to print them to the console. Now, writing them back to an attribute is pretty straightforward. We could say f@test equals area. And if we do that, then it will of course create a new attribute that contains the value that was inside this local variable. Next to that, we can also use the printf command. And printf will effectively print for every single time the loop runs, every single primitive we're running over, a new value. Now, if we go ahead and type within quotation marks something like primitive area, and because this is a expression, we need to put a semicolon behind it so it doesn't error out, then this will write out that particular line of text to the console. Now, because it's only a single line of text and it's repeated over every single primitive, VEX is at least smart enough to not give it to us, how many different times? So that's nice of VEX, right? Not to give us a massive list of primitive area here. But the moment we feed it a value, and we can do this by typing %d, and then behind our quotation marks, we can type the value that we wanted to set. So in this case, that will be the area local variable. It is going to write it out for every single value. And it's also going to stick it all together. So if you want to make this a little bit easier to read, you could also type \n for a new line, and this will put it one for every single line, so you can organize it a little bit. Now, I do advise you to be careful with this way of writing out information, because if you have a lot of primitives, writing text out to the console will take some time and it will slow Houdini down. Even if your VEX script is really fast, and VEX is fast, this will make it a lot slower, because every single time it runs over a primitive, it's going to write out a line, and that will take some time to process. Okay, so yeah, be careful with large amounts of geometry when you're using this, but this is one way to write it out, and we'll use this more for debug later in the masterclass as well. But now that we have this, I also would like to quickly grab my current interior grid scale and also send this out to its own local variable. Now we can do this, of course, by creating another float, and I'm going to call this one the grid scale. And instead of referencing my float attribute, I'm simply going to grab a channel float value, and I'll call this one grid scale. So then if I go over here, I click on that button, I will create a grid scale parameter. Then from my parameters panel, let's grab the interior grid scale, copy that, and let's plug it in here. So now this value will be set. Now, of course, at this point, we can't read out this value. So let's create a simple test attribute here. And now if I look in the bottom, we can see we have a test variable available. So that's working. And then let's go ahead and take this grid scale and let's multiply it by the power of 2. So we can simply do that using a power expression. So the power expression takes the first argument, that is this part here, our grid scale parameter reference. And then we can take a second argument and multiply it by the power of that. So we type comma, and then to the power of 2. So now down below here you can see 4 just became 16. Okay, pretty simple. Okay, so next we need to actually write the condition that takes these values, and if that condition is true, removes the primitive. Now, like I showed you here, we write it using an if statement, then whatever piece of code we have compared to something else. And then inside curly brackets, we can then write a new set of VEX script that executes if this is true. So in our case, we're going to remove our primitive. Let me quickly run you through this. So like I said, we write an if statement. And then inside here, I want to write my comparison that I described earlier. So we take the current area size for our primitive. We subtract with that the current grid scale. And then, wrapped inside of an absolute bracket, it will always return a positive value. And if the difference is too big, it will be a larger value than our threshold value here, right? So we can simply write if the grid scale minus the area wrapped inside of our absolute expression is greater than 0.001, then inside curly brackets we can write our remove primitive expression. Now the remove primitive expression, let's write that, is simply going to take whatever geometry you feed it. We can type 0 for the current geometry. Then we want to specify the current primitive number we want to remove. In this case, that's the actual current primitive number. So we can type @primnum, which will reference the primitive this loop is currently running over. And then the last argument of this VEX expression requires us to say if it should remove the points that belong to the primitives that it removed or not. Now, I don't want it to leave around a bunch of primitiveless points when we remove the primitive. So I'm going to say yes, a value of 1, basically. And then we have to semicolon it up. You notice how we didn't have to put a semicolon at the end of the if statement. And that's basically because an if statement is still one function. So we don't have to close it off. but we do need to close the individual functions inside of the if statement, like this. And as you can see, this actually works. We did remove all of the primitives on the outside that were just too small, but these values here that aren't exactly 16, but very close to it, were kept. So that's working. Okay, great. Now let's get rid of our test attribute here as well. Now, next what we need to do is take these primitives, and I want to retrieve their center points. But before I do that, I still need to clean them up, and I'll show you why. Now at this moment, our grid is slightly offset, and because of that, it's not quite overlapping any of these edges. But if I just return this back to a default value, like 0, then you'll notice that in some cases, we are going to cut right on the corner of this edge. And when that happens, our primitive here is going to receive 5 vertices, or 5 points. Notice how this particular number here in the middle of this primitive is not quite centered on the center of the primitive. And that has to do with the center of gravity of this primitive. Basically, the total distribution of points on a primitive determines where its center is. And that's actually reflected by its primitive number, right? Now, if we want to retrieve the center of a primitive, we can do this really easily using an attribute wrangle. Let's create one. And let's call this one the create center point. Now we do need to run this over our primitives, of course, so let's switch it over to that. And then in here we can use the add point VEX expression. And the add point VEX expression requires us to specify which geometry we want to set it on. In this case that would be input 0, our main geometry. And then we need to specify the location that we want to add this point to on this primitive. So in this case, we can write v at p, or the current point position, to sample the point position of every single point on this primitive, and then grab its average location. Okay, so if we do that, and we close this with a semicolon, notice how it's actually created a point in the center of each of our primitives, including over here. Notice how this primitive has 5 points. And that means that, of course, it also has 5 vertices. So this point currently is not located in the center because it's being pulled by this point here. Now, we can fix this. We can clean it up really quickly by simply grabbing a facet node. And then we can plug that in. And let's call this one remove inline points. We've done this before. And then let's turn on the option right there. As you notice, immediately the point jumps to the center, because right now this particular primitive just has points on its corners, no longer in the middle of this line. And that of course restores the center of gravity on this primitive. Okay, so with this VEX script, we have our points, but we also still have these primitives as well. Now we can easily remove those using the same remove primitive function from before. So let's type that. Remove primitive, current geometry, current primitive number, and then let's remove all of the points as well. So let's give it a value of 1. And that will remove every single primitive, but keep the points we just created in the line above intact. So you might notice that it's only removed the primitives that were present at the very start, because those were primitive numbers that already existed at that point. But we're not removing these new points. I'll leave this here for now, but I quickly want to look at a different method to create these points without having to first clean our centers, right? Our center of gravity. And that is by using a extract centroid node. And the extract centroid node basically allows us to grab the center point of any selection of primitives that share the same attribute value. Now we do actually have to provide a unique attribute value for this to work. So over here, right now it's looking for a value called name, which doesn't exist, so it is going to error out on us. But we can fix this really quickly. Let's go to the attribute Wrangle node here. And inside of our code, I am simply going to create a new attribute called integer attribute valid piece. And then I'm going to grab the current primitive number. So let's say at primnum and then semicolon. And this will simply write out a new attribute, one for every single primitive, a unique one for every single primitive. And they don't quite match the exact number, but that's simply because we did remove some of our primitives after all, so that's to be expected. Then we can go ahead and grab this new attribute, and let's just feed it into the extract centroid node right there. Okay, so now we do have center points. And let's say we look at this point here again. Now you can see it's still offset. It's not quite in the center, just like the other ones. It's a bit hard to see, but let's say I grab this extract centroid node and I switch it over from center of mass to bounding box center. And now we see the difference, right? So the bounding box center simply creates a point at the center of the bounding box of this primitive, of this attribute group here, this primitive. And center of mass does whatever the add point here did. So in this case, we don't actually need the facet node, but just to keep it clean, I'm still going to do it, right? So let's say we plug it in like that. Alright, so at this stage we now have our points, and we also have our interior grids, and they're all functioning properly. We can scale them up, and no matter their size, they will work. We can offset them as well, and that's all working just fine. Next to that, each one of these grids, if they're whole, is creating a point. So now we have the basic information that we need in order to start placing our elevators and our staircases. However, we've already covered a lot in this video, including several sections of VEX, like this and here. And if I were to continue on at this stage and build the rest of this component out in this video, we'd probably be here for another hour. So what I'm going to do is split this video in two. The next stage that we will have to build in the second half of this lecture video, is going to be to create the inputs for our elevators and our staircases, and then to snap those to the grid and aim them in the direction of the current point of that grid tile. Then we are going to take that and we are going to add the boxes to them, specifically the elevator and the staircase, and they need to be offset and properly positioned as well. And then finally we'll use that to cut our floors so we can punch some holes into that. So with that, thanks for watching this video. I hope to see you in the next one, and have a good one.